Hello everyone, my name is Anthony Shivkumar, and in today's video I'm going to do a follow-up of the Maxwell's equation, and it's still equation 1, but today we're going to deal with the differential form. So in the previous video we spoke about the Maxwell's equation, but we spoke about the one in the integral form, and just to recap, the integral form talks about the flux, which is basically the amount of electric field that is penetrating through a surface area, or the amount of electric charge that is present around the surface of a real sphere or real area, or it could be imaginary, and that's the flux, and that is equals to the total amount of charge that's enclosed divided by the permittivity of free space. So this is the integral form of Maxwell's equation, which is also known as the Gauss law. And in today's video, we're going to talk about the differential form. And the differential form is taking basically the derivatives. And here we have the differential form dot E, the electric field, is equals to the charge density coulombs per cubic meter divided by the permittivity of free space. Now, what is the actual difference between the integral form and the differential form? So once we kind of understand this intuitively, we'll be able to understand what the equations really are trying to tell us. So the integral form describes the electric or magnetic field over a surface or around a loop. So that's talking about a surface area. Whereas the differential form talks about the instance or an individual point. It tells you how a specific electric field or magnetic field behaves at a specific location in space. So the integral form is around an area, whereas the differential form is around a single point. And what does that single point really tell us? And this is the equation that basically tells us what happens at that single instance. Now, there are a few things to note about this equation. So this is the differential operator, also known as the nabla, or the differential operator, the differentiation. And we're doing a dot product on the electric field, which is Newton per coulomb. We spoke about this in the previous video, which is equals to the charge density divided by permittivity. So let's focus on this area, this part of the equation, and what it's really trying to tell us. So in differentiation, and when we're dealing with vector products, so this is a vector, the differential operator on a vector, the dot product on an electric field, which is also a vector. So when you have when you're differentiating a particular quantity, there are three types of quantities where you can do a difference that you can take the derivative of. If you just take the derivative of a scalar, you're going to get a gradient. Now you'll realize, if you do any machine learning or if you do any form of optimization problems, you find an algorithm called gradient descent or a slope of a line, and that's just basically, if I take a derivative of a slope of a line which has some slope, that'll be a gradient, and that's what this particular differentiation operator would do. In this case, we are doing a dot product of a vector. So when you talk about a vector, we have something called as divergence or convergence. And divergence is, if you have a dot product, it will give you a scalar quantity. So if you take a dot product of two vector quantities, it will give you a scalar quantity, and that value will tell you whether at that instance whether you have something emitting or something converging at that point. And this is important to know, whether at a very instance whether all the vector fields is coming in or is going. If it's coming in and is converging, or if it's going out, then it's diverging. So that's what a dot product of a scalar does, and this is what this particular equation is dealing with. And if it's a cross product, which is another vector quantity. So the cross product of two vectors will give you a vector, which means it's got magnitude and direction. You'll have something called a curl, and this would be more relevant in equations 3 and 4 of Maxwell's equations. But what we're dealing with is divergence. So when we do a derivative over a dot product in Maxwell's equation, we are talking about the divergence or the convergence. So the divergence. So what exactly is a divergence? And a divergence is, as I mentioned, at a very specific point, we want to know what all vector fields are around this area or around around the vicinity of this particular point. And if you add up all the vector fields that are the cumulative vector fields that are impacting this particular point, whether it's diverging or whether it's converging. And that's what the differentiation operator will do. Because it's, as I mentioned, it's a scalar quantity, it'll give you a value, and that value would tell you the intensity at that very instance. And if it's positive, that means it's diverging, and if it's negative, it'll be converging. That means it is all the electric fields is approaching that particular instance rather than emitting from that instance. Now, to really understand that equation, let's dig a little deeper. So the del dot A, or the divergence of this particular product, if I just take a del dot A over here, what we're doing based on the original equation of the integrator form, we know that A dot N dA is the flux. And a flux is basically the amount on a surface area. Now, if I take the amount of flux on a surface area and divide it by the volume, and I keep decreasing the volume to as close to 0, that will give me the divergence at that very instant. So you're basically taking the flux over divided by the volume, and the volume of a very small instance, and that will basically give you the divergence. So this is in a high level nutshell what this is trying to do, is taking the integration form, but with dividing it over a very, very small volume at that very instance, and that will tell you whether the vector field over there, the electric field over there, is diverging or converging. But this is not a very practical equation to really make sense of, in the sense that there is a better and intuitive way to understand this, and so we won't be doing limits and integration when we deal with this. What we want to do is, I've basically noted this down, that because A is a vector quantity, it's going to have magnitude and direction, and it's going to have magnitude and direction in 3D space. So it's going to be in the XYZ direction. And in the Cartesian form, we have the I of the X direction, the J in the Y direction, and the K hat in the Z direction. And if these are the quantities of the X direction, and this is the vector field, and an A in this case could very well be the electric field, and it'll be the electric field acting in the X direction, the electric field acting in the Y direction, and the electric field acting in the Z direction. So I dot I is going to be 1, but I dot J is going to be 0, or K dot J is going to be 0. So I cannot, if I do multiply I into, say, J, is going to be 0. So only the I dot I is going to be 1. So eventually it turns out to be a partial derivative with respect to X. The X component is going to be a partial derivative of the A with respect to X, partial derivative of Y with respect to Y, and partial derivative of Z with respect to Z. Now, since this is a scalar quantity, we got to add all of this up, and it'll give us a value. And that's what this del dot A equals to. And that's what, in a nutshell, is what's happening at a differential form of Gauss's law. So let's take an example right now. So I've got MATLAB in here open, and what I want to show you is an example of what really is happening in terms of vector fields. Now, because I'm dealing with say a robotics problem, the mathematics of Maxwell's equations actually comes the fundamental concept of Maxwell's equation. Though we're dealing with vector fields, and though we're dealing with, say, fields and flow in the electric field, This is also very relevant in, say, things like aerodynamics and how air flows through, say, the propeller blades, and the whole idea of what's the direction of the wind over a surface of an area. And these types of equations are prevalent even in the mechanical aerodynamic world, not just in the electrical and electromechanical world. So the math and the concepts over here is very transferable to other applications. In this particular case, we're dealing with the electromagnetism, and this will be applicable in designing motors, understanding how capacitors, and even designing PCBs at least at a fundamental level. Solving these equations day in and day out won't be very practical. That's where you have simulation tools which basically take these concepts and implement them. But what I want to show you is an example of how we can represent this vector fields, as I showed over here, at a particular instance, and how it would look like. And this type of understanding will also be transferable to other applications in science. So there is a command over here which is called a quiver. So I'm just going to do something called as a help quiver. And here we have something that plots the velocity vectors as arrows with components. So this is an example of a command that you can use in MATLAB, where you can plot basically vector fields. You can also go to MATLAB and just type in on the online documentation types of quiver, and it'll give you the definition and how to use this particular command. So I'm just going to take an example from here to just show you what really it is doing. So I'll give an example of so I have an equation. I'm just going to give you an equation. So we're going to put a mesh grid, and we're going to put the u component is going to be sine y, and the y component is going to be sine x. And here I am going to show you a quiver. And here I'm just taking the example from MATLAB itself, and we'll just plot an example over here. And what you see over here is that MATLAB is basically, in a nutshell, what it's really doing in this particular case, because this is what convergence and divergence is all about, that we're taking an example of the space map or a mesh grid of basically x and y, and the values of u, or the x component, is nothing but sine y, and the value of, say, the y component is cos x. So in this particular case, as you move across the x direction, you'll see that the y increases or decreases, because it is sinusoidal over here. And as you move across the y direction, it is very sinusoidal, or it's cosine or cosine in this particular direction. And then when you do a quiver, it'll tell you, it'll basically plot the arrows at every single instance. So if I take this particular point over here, it'll tell me whether the vector field is pointing outwards or whether the vector field is pointing inwards. And if the vector field is neither pointing outwards or inwards, then it'll just be a 0 basically. So every instance of a point over here will tell you not just it'll give you the instance or the magnitude of that vector field. So if it's positive, it's going to be it's radiating outwards, and once it's radiating outwards, then you basically are trying to figure out the intensity of that vector field, which is nothing but the magnitude, and that's basically what the divergence of Maxwell's equation in differential form will tell you. So you'll see that the longer the arrows, the more powerful the electric field is. In this particular case, it's not, but this is what say, for example, you had a magnet over here and you wanted to check the electric field around it, or you had a charge over here rather, and you wanted to check the electric field around it. The longer the line means there's more charge around this particular area penetrating through through a surface, and if the arrow is small, that means it is a less in magnitude, it's weaker, and if it's not there, then it's basically a 0. So yeah, So you could have, say, a quiver. So for example, if I have, say, an electric field which is going very sinusoidal in nature, so I want to figure out at every instance what's really happening. So let's say I have a function such as I have actually have a function over here in my history, and let's say I want to do a quiver on, say, let's say I have a function over here and I want to do a quiver on, say, yeah, this one. So it's just going to be in one direction. It's just going to be across the x direction, and the electric field is basically, penetrating. It's very sinusoidal in the sense, it's basically going up and down, and I want to figure out the divergence at that very instance. So if I do a thing based on, so let me just take this as what we have over here. So it'll be x, and say there's no y component. So yeah, so for if I have a sinusoidal electric field that's ranging in magnitude sinusoidally, basically, and if I had to plot at every instance how that electric field, what's the divergence at every instance, you'll realize that since it's a sinusoidal, and the derivative of a sinusoidal will be cos, because that will be the divergence. And the divergence at every instance, and if I had to plot that divergence over this whole area, which will give me the magnitude. If it's negative with the magnitude, then it'll basically make a longer arrow. And because it's only in the x direction, it'll tell me the magnitude at that particular instance. That's what's happening over here. So it's basically going at a high value, and then it's going to go, then it's 0. Then it picks up zeros, then it increases kind of like cosine, and then it increases, and then it changes direction, and then it becomes 0, and then it again oscillates between high, low, high, low, high, low, high, low. So if you have a vector field that's very sinusoidal in magnitude, if you take the divergence of that at a very instance, it will tell you whether it's converging or whether it's diverging. So at this particular instance, it is going away, so it is basically diverging, and if the arrow is coming inwards, then that means it is converging. So the direction of the arrow, or the positive or negative, will tell you whether it's converging or diverging, and the magnitude will basically tell you the strength of the arrow, or the strength of the field. And in this particular case, it will tell me the longer the arrow, the stronger the field, and the shorter the arrow, the weaker the field. And that's what the differential form of the first equation of Maxwell will tell you. It will give you the exact instance of what's happening of the electric field at a very specific instance, at a very specific point, and it'll give you the magnitude, and you'll be able to figure out whether it's converging or whether it's diverging based on this formula. And that's about it. I thought it would be interesting to do all 4 equations this way, do some simulations, and then eventually figure out more practical ways of how I would use them, say in applying it to designing, say, the brushless DC motor, where understanding how do you design the air gap, how do you design the slots, how do you design the lamination and the number of coils over the stator, the windings. All of this will help me design a better brushless DC motor, and then the fundamentals of what's happening under the hood with every electromagnetic, any product that deals with electromagnetism, Maxwell's equations is governing them. And I thought that would be a good idea to just go through these equations and then get to the practical applications of it. So if you like these videos, do like them and subscribe. And and until next time, thank you so much.